Good evening, and welcome back to The Resting Researcher. Tonight, we're traveling to the edge of space, to a place where Earth's atmosphere meets the solar wind, where invisible particles collide with gas molecules to create one of nature's most spectacular light shows. We're exploring the Aurora, the northern and southern lights, those shimmering curtains of green, purple, and red that dance across polar skies, visible on clear winter nights to anyone patient enough to look up. Before we begin our journey, I'd love to know where you're watching from tonight. Have you ever seen an aurora in person? And if these calm explorations help you unwind, please consider subscribing. It helps others discover this peaceful approach to science. I hope this exploration of Earth's light show is captivating enough to hold your attention, yet gentle enough to guide you toward rest. And if you do stay awake through it all, at least you'll understand what causes those dancing lights that have mesmerized humans for thousands of years. So settle in, get comfortable, and let's journey upward to the thin boundary where our planet meets space, where solar particles paint the sky in colors that shouldn't exist in darkness. To understand the aurora, we need to start 93 million miles away, at the Sun. The Sun isn't just a ball of light. It's a massive sphere of plasma, superheated gas so hot that electrons have been stripped from their atoms. This plasma churns and boils, driven by nuclear fusion in the cores and convection currents that carry heat to the surface. The Sun's surface, called the photosphere, has a temperature of about 5,500 degrees Celsius. But the atmosphere above it, the corona, is even hotter, over 1,000,000 degrees in places. Scientists still don't fully understand why. This extreme heat means particles in the corona move incredibly fast, so fast that some of them escape the Sun's gravity entirely, streaming out into space as a constant flow called the solar wind. The solar wind is mostly made of electrons and protons, along with some heavier ions. These particles travel through space at speeds of 300 to 800 kilometers per second, taking about 3 to 4 days to reach Earth. But the solar wind isn't constant. It varies depending on solar activity. And sometimes, the Sun releases much more dramatic bursts of particles. These are called coronal mass ejections, or CMEs. They occur when magnetic field lines on the Sun's surface twist, tangle, and suddenly snap, releasing enormous amounts of energy and billions of tons of plasma into space. If a CME happens to be directed toward Earth, those particles arrive in a dense, fast-moving wave, far more intense than the normal solar wind. Now, you might wonder why we're not constantly bombarded by these particles. Why, Thomas, the solar wind doesn't strip away our atmosphere or harm life on the surface? The answer is Earth's magnetic field. Deep inside the Earth, about 3,000 kilometers down, molten iron flows in the outer core. This moving, electrically conductive liquid generates a magnetic field that extends far out into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects most of the solar wind, channeling it around Earth, like water flowing around a rock in a stream. Without it, our atmosphere would slowly erode, just as Mars's atmosphere has, over billions of years. But the magnetosphere isn't a perfect shield. Near the poles, the magnetic field lines dip down toward Earth's surface, creating pathways where solar particles can funnel into the upper atmosphere. And that's where the aurora begins. When charged particles from the solar wind follow these magnetic field lines into the polar regions, they collide with gas molecules in the atmosphere. Mostly oxygen and nitrogen, the two most abundant gases. These collisions transfer energy to the gas molecules, exciting their electrons into higher energy states. When the electrons drop back to their normal state, They release that energy as light, specific wavelengths, specific colors, depending on which gas is involved and how much energy was transferred. Oxygen produces green light when excited at lower altitudes, around 100 to 150 kilometers up. At higher altitudes, above 200 kilometers, oxygen emits red light. Nitrogen produces blue and purple hues. The result is a glowing curtain of light stretching across the sky, shimmering and shifting as the flow of particles changes. The aurora isn't a solid object. It's a luminous region, a zone where millions of collisions are happening every second, each one producing a brief flash of light. Together, those flashes create the appearance of a continuous glow. And because the solar wind is never perfectly steady, the aurora moves, it ripples, it pulses. Sometimes it forms arcs that stretch from horizon to horizon. Other times, it breaks into rays, vertical columns of light that seem to reach down toward the ground. On particularly active nights, during strong geomagnetic storms, the aurora can cover the entire sky. It can move so quickly that observers report seeing it dance, swirling and folding like fabric in the wind. Historically, people didn't understand what they were seeing. In Norse mythology, the aurora was believed to be the reflection of the Valkyries' armor as they led fallen warriors to Valhalla. Some Inuit cultures thought the lights were spirits of the dead, playing games in the sky. In medieval Europe, red auroras were sometimes seen as omens, blood in the sky foretelling war or disaster. Even in the 19th century, after scientists began to study the phenomenon systematically, there was debate about whether the aurora was an atmospheric or a magnetic effect. It wasn't until the 20th century, with the advent of satellites and a better understanding of the sun, that the full picture came together. The aurora is the visible consequence of our sun's constant output of energy and particles interacting with Earth's magnetic shield. It's a reminder that even though space seems empty, it's filled with invisible forces, magnetic fields, particle streams, radiation. And sometimes, under the right conditions, those forces become visible, painting the night sky in colors that seem almost impossible. As we pause here, picture the journey those particles take. Born in the chaos of the sun's corona, accelerated to incredible speeds, traveling for days across the void, only to spiral down Earth's magnetic field lines and collide with oxygen molecules, releasing a brief flash of green light before dissipating into the night. Every aurora is the end of a journey that began 93 million miles away. The aurora's colors aren't random. They are determined by the physics of atomic excitation, by which gas molecules are involved, and how energetic the collisions are. Let's start with green, the most common aurora color. This comes from oxygen atoms at altitudes between 100 and 150 kilometers. When solar particles strike these oxygen atoms, they excite electrons into a higher energy state. About 1 second later, the electrons drop back down, releasing a photon of green light with a wavelength of 557.7 nanometers. 1 second might seem fast, but it's actually quite slow for an atomic process. Most atomic transitions happen in millionths or billionths of a second. Oxygen's green emission is what's called a forbidden transition, one that normally wouldn't occur because of quantum mechanical rules. But in the thin upper atmosphere, where collisions between atoms are rare, the excited oxygen has time to emit light before something else disrupts it. At higher altitudes, above 200 kilometers, oxygen produces red light instead. This transition is even slower, taking up to 2 minutes. The wavelength is 630 nanometers, a deep red that's often faint and hard to see with the naked eye, unless the aurora is very strong. Nitrogen contributes blue and purple colors. When nitrogen molecules are struck by solar particles, they emit light at several wavelengths, creating blue and violet hues that often appear at the lower edges of the aurora. The altitude of the aurora matters not just for color, but for shape. Most auroras occur between 100 and 300 kilometers above the surface. Below 100 kilometers, the atmosphere is too dense. Incoming particles collide with so many molecules that they lose energy quickly and don't penetrate further. Above 300 kilometers, the atmosphere is so thin that there aren't enough molecules to produce visible light. The shape of the aurora is influenced by Earth's magnetic field. Near the poles, magnetic field lines converge, funneling particles into concentrated regions. This is why auroras typically appear as arcs or bands, aligned roughly east-west. These arcs mark the boundary of the auroral oval, a ring-shaped zone centered on each magnetic pole. The oval expands and contracts depending on solar activity. During quiet periods, it's small and stays close to the poles. During geomagnetic storms, it can expand dramatically, bringing auroras to latitudes where they're rarely seen. Sometimes the aurora forms curtains, vertical structures that look like hanging drapes. These form when particles stream down, along field lines that are nearly vertical. The curtains can ripple and wave as the particle flow changes, creating the dynamic motion that makes auroras so mesmerizing. Other times, the aurora breaks into rays, narrow columns of light. These often appear during the most active phases of a display, when particle flows are particularly intense. And then there's the corona effect, when the aurora appears directly overhead. To an observer on the ground, the rays seem to converge at a point in the sky, radiating outward like the spokes of a wheel. This is an effect of perspective, the three-dimensional structure of the aurora projected onto the dome of the sky. The brightness of the aurora varies widely. On a scale developed by researchers, auroras range from a faint glow barely visible to the naked eye to brilliant displays bright enough to cast shadows. The faintest auroras, called aurora in the first stage, are often just a pale arc on the horizon, easy to mistake for light pollution. These occur during low solar activity, when the particle flux is minimal. The brightest auroras in the fourth stage are vivid and fast-moving, covering much of the sky with rapidly shifting colors. These happen during major geomagnetic storms, often triggered by coronal mass ejections from the sun. Now, let's talk about timing. Auroras don't appear randomly. They follow patterns linked to solar activity. The sun goes through an 11-year cycle of activity, from solar minimum, when sunspots and CMEs are rare, to solar maximum, when the sun's surface is covered with active regions, producing frequent eruptions. During solar maximum, auroras are more common and more intense. They occur at lower latitudes, sometimes visible as far south as the northern United States, or even further. During solar minimum, auroras are less frequent and usually confined to higher latitudes, close to the Arctic and Antarctic circles. But even within this cycle, auroras follow shorter patterns. They're more common around the equinoxes in March and September. Scientists believe this is due to the angle of Earth's magnetic field relative to the solar wind, which allows particles to enter the magnetosphere more easily during those times. Auroras are also more likely to appear a few days after a large solar flare or CME. Monitoring the sun allows scientists to predict when Earth might be hit by a particle stream, giving aurora chasers a few days' warning to prepare. Modern space weather forecasting uses satellites positioned between Earth and the sun to detect incoming CMEs. When a fast-moving cloud of plasma is spotted, alerts go out, and people at high latitudes watch the skies, But even with predictions, auroras remain unpredictable. A storm might arrive and produce nothing, or a minor event on the sun might trigger a spectacular display. The magnetosphere's response to solar wind is complex, influenced by factors scientists are still working to understand. What's certain is that every aurora is unique. No two displays are identical. The colors, shapes, and motion depend on the specific conditions at that moment. The energy and density of the incoming particles, the state of Earth's magnetic field, the compositions and temperature of the upper atmosphere. As we settle here, picture the delicate interplay of forces required for an aurora to appear. Particles from the sun, guided by invisible magnetic fields, colliding with molecules in the thinnest layers of the atmosphere, releasing light that travels down to the ground, where someone standing in the cold night air looks up and sees green curtains rippling across the sky. It's a chain of events that stretches from the heart of the sun to the surface of the earth, all culminating in a few hours of light in the darkness. Earth isn't the only planet with auroras. Anywhere there's a magnetic field and an atmosphere, auroras can form. And the solar system is full of them, each one revealing something about the planet it illuminates. Let's start with Jupiter, which has the most powerful auroras in the solar system. Jupiter's magnetic field is enormous, 20,000 times stronger than Earth's, and it extends millions of kilometers into space. The auroras on Jupiter aren't just powered by the solar wind. They are also driven by Jupiter's own rotation. The planet spins so quickly, once every 10 hours, that its magnetic field sweeps through the surrounding space, accelerating charged particles and flinging them toward the poles. Additionally, Jupiter's moon Io is volcanically active, spewing sulfur and oxygen into space. These particles get caught in Jupiter's magnetic field and ionized, becoming part of a vast plasma torus that encircles the planet. When these particles spiral down toward the poles, they create auroras far brighter and more energetic than anything seen on Earth. Jupiter's auroras are mostly in the ultraviolet spectrum, invisible to the human eye, but detectable by spacecraft and space telescopes. They form permanent ovals around both poles, glowing continuously with brightness fluctuations depending on solar wind conditions and the position of Io in its orbit. Saturn has auroras too. Like Jupiter, Saturn's auroras are driven by a combination of solar wind and internal processes. The planet's rotation and its interactions with its moon Enceladus, which ejects water vapor into space, contribute to the auroral activity. Saturn's auroras also appear primarily in ultraviolet light, forming rings around the poles that expand and contract in response to changes in the solar wind. Interestingly, during Saturn's equinoxes, when sunlight strikes the ring's edge on, the auroras behave differently. The rings cast shadows on the planet's atmosphere, cooling it and altering how auroras form. It's a reminder that even on other worlds, auroras are sensitive to local conditions. Uranus and Neptune, the ice giants, also have auroras, but their magnetic fields are unusual. Unlike Earth, Jupiter, and Saturn, where the magnetic poles are roughly aligned with the rotational poles, Uranus and Neptune have tilted magnetic fields that are offset from their centers. This creates auroras that don't stay in fixed positions. Instead, they move around the planet as it rotates, appearing at different latitudes and longitudes. Observations from the Hubble Space Telescope have captured these wandering auroras, offering clues about the planet's internal magnetic dynamics. Even Mars has faint auroras, despite lacking a global magnetic field. Mars lost its magnetic field billions of years ago, leaving its atmosphere exposed to the solar wind. but localized patches of magnetized crust remain, particularly in the southern hemisphere. When solar particles interact with these magnetic anomalies, they can create small, patchy auroras that don't follow the organized patterns seen on Earth. These Martian auroras are very faint and occur at unusual locations, sometimes near the equator rather than the poles. Venus has auroras too, though they're even stranger. Venus has no magnetic field and rotates so slowly that it doesn't generate one through internal convection. But the solar wind interacts directly with its thick atmosphere, creating diffuse auroral glows on the planet's night side. These Venusian auroras are irregular and patchy, lacking the structure of Earth's auroras. They offer a glimpse of what Earth's auroras might look like if our magnetic field disappeared. Beyond the solar system, astronomers have detected auroras on exoplanets, planets orbiting other stars. Some of these exoplanets are hot Jupiters, gas giants orbiting very close to their stars. The intense stellar wind and powerful magnetic interactions create auroras far more luminous than Jupiter's, possibly visible in radio wavelengths from Earth. Detecting these distant auroras helps scientists understand the magnetic fields and atmospheres of exoplanets, worlds we may never visit but can study from afar. Even some moons have auroras. Ganymede, Jupiter's largest moon, has a weak magnetic field of its own. When particles from Jupiter's magnetosphere strike Ganymede's thin atmosphere, they create faint auroral glows near the moon's poles. It's a nested system, Jupiter's magnetic field, interacting with Io's volcanoes, with Ganymede's field, with the solar wind, all creating layers of auroral activity throughout the Jovian system. Back on Earth, scientists study auroras not just for their beauty, but for what they reveal about space weather. Auroras are a visible sign of geomagnetic activity, which can affect satellites, power grids, and communication systems. During strong geomagnetic storms, induced currents can flow through power lines, potentially causing blackouts. Satellites in low Earth orbit experience increased drag as the atmosphere expands slightly during heating from auroral activity. GPS signals can be disrupted as the ionosphere becomes turbulent. Understanding auroras helps predict these effects, allowing engineers and operators to take protective measures. It's one reason space weather monitoring has become a priority for governments and industries. As we pause here, imagine the variety of auroras across the solar system. Green curtains on Earth, ultraviolet rings on Jupiter, wandering glows on Uranus, patchy flickers on Mars, each one a light show shaped by local conditions, magnetic fields, and atmospheres, but all driven by the same basic process: charged particles colliding with gas. It's a universal phenomenon, occurring wherever the right conditions exist, and as we discover more planets around other stars, we'll likely find even more varieties of auroras, light shows we can't yet imagine. For thousands of years, people have looked up at polar skies and seen the aurora. For most of history, they didn't understand what caused it, but they recognized it as something extraordinary. To witness an aurora in person is to experience something that connects you to those ancient observers. The same lights they saw, born from the same solar storms, appearing in the same patterns. If you want to see an aurora, there are a few things to know. First, location matters. Auroras occur most frequently near the auroral ovals, rings centered on the magnetic poles. In the northern hemisphere, this includes northern Scandinavia, Iceland, northern Canada, and Alaska. In the southern hemisphere, it includes Antarctica and the southern tips of South America and New Zealand. The farther north or south you go, the more likely you are to see auroras. In places like Tromsø, Norway, or Fairbanks, Alaska, Auroras are visible on more than 200 nights per year during the dark season. But during strong geomagnetic storms, the auroral oval expands, bringing auroras to lower latitudes. People in the northern United States, Scotland, or northern Europe can sometimes see them, especially during solar maximum. Timing also matters. Auroras are most visible during the dark months, when nights are long. In the Arctic, this means roughly September through March. Summer's endless daylight makes auroras invisible, even though they're still occurring overhead. Within a single night, auroras are most common around midnight, though they can appear at any time after dark. Activity often peaks in the hours after midnight. Weather is crucial. Clouds block the view, so clear skies are essential. Light pollution also interferes. Cities with bright streetlights make it difficult to see faint auroras. Dark locations far from urban areas offer the best viewing. Once you're in the right place at the right time, patience is required. Auroras don't appear on command. You might wait for hours, or you might step outside and see them immediately. When they do appear, they often start as a faint greenish glow on the northern horizon. It might be easy to dismiss as light pollution or clouds, but if you watch, it gradually intensifies. The arc brightens, motion becomes visible, ripples and waves. Then, if conditions are right, the display escalates. The arc breaks into curtains. Colors appear, purple edges, hints of red. The curtains move, swaying and folding. Sometimes rays shoot upward, vertical columns reaching toward the zenith. On the most active nights, the entire sky fills with light. The aurora forms a corona overhead, rays radiating from a central point. Colors shift rapidly. The motion is so fast it's almost disorienting. And then, as suddenly as it started, it fades. The curtains dissolve into a faint glow. The sky darkens again. The show is over. Photographing auroras has become popular, and modern cameras can capture colors and details invisible to the naked eye. Long exposures reveal reds and purples that appear faint in person. The camera's sensor integrates light over several seconds, while the eye sees only a snapshot. This means photographs often look more vibrant than the real experience, but the real experience has something photographs can't capture. The sense of motion, the immediacy, the feeling of standing beneath something vast and elemental. People who've seen strong auroras often describe them as one of the most memorable experiences of their lives. There's something humbling about watching the sky come alive, knowing that what you're seeing is the sun's energy, transformed by Earth's magnetic field and atmosphere into light. Indigenous peoples in the Arctic have lived with auroras for millennia. They've woven them into stories, songs, and traditions. For some, the lights are ancestors or spirits. For others, they're omens or playful beings. Modern science has explained the mechanism, but it hasn't diminished the wonder. If anything, understanding the vast scale of the process, from solar storms to atmospheric collisions, makes it more astonishing. As space tourism develops, some companies are offering flights to high altitudes, where auroras can be seen from above. From that perspective, the aurora is a glowing curtain below you, draped across the curve of the Earth. Astronauts aboard the International Space Station regularly see auroras from orbit. They describe them as one of the most beautiful sights in space. Ribbons of green and red stretching across the planet's limb. For most of us, seeing an aurora means traveling to remote places and waiting in the cold. But the effort is worth it. To stand beneath the aurora is to witness one of nature's grand performances, a light show powered by the sun, shaped by Earth's magnetism, and visible only because of the precise conditions that exist in our upper atmosphere. As we come to the end of our journey through the science of the aurora, let's reflect on what we've learned. The aurora is more than just a pretty light show. It's a visible manifestation of invisible forces, solar wind, magnetic fields, atomic collisions, all of them working together to paint the sky. It's a reminder that Earth is not isolated. We exist within the sun's extended atmosphere, constantly bathed in particles and radiation. Our magnetic field shields us, but it also channels that energy into the auroras, turning a potential threat into something beautiful. Every aurora is a reminder that we live on a dynamic planet, orbiting an active star. The lights we see tonight might be the result of a solar storm that happened 3 days ago, a burst of energy that traveled millions of miles to reach us. The next time you hear that a geomagnetic storm is expected and auroras might be visible at lower latitudes, consider stepping outside, away from city lights, into the cold, and looking up. You might see nothing, or you might see a faint glow. Or, if you're very lucky, you might see the sky come alive with color and motion, curtains of light rippling overhead, shaped by forces far beyond human control. Thank you for joining me on this exploration of the aurora. I hope it gave you a deeper appreciation for the delicate interactions that create one of Earth's most beautiful phenomena. As you drift towards sleep tonight, picture those curtains of light dancing across polar skies, solar particles spiraling down magnetic field lines, oxygen atoms releasing green photons, the quiet beauty of physics made visible. And rest easy knowing that even now, somewhere in the Arctic or Antarctic night, the aurora is glowing, painting the sky for anyone patient enough to watch. Sleep well,